welcome to everyone for coming to this quantum space-time seminar. And today we are very happy to have Sergei Dubovsky from New York University, and he's going to tell us about 3D glue balls versus closed effective strings. Over to you, Sergei.
Okay, thanks a lot for the invitation to give this talk, and sorry for the confusion with scheduling. And yeah, I have mixed feelings. On one hand, it's great, like Zoom opportunity that we can talk from different parts of the world and give these talks. But on the other hand, I just been at my first post-COVID conference, which was in person, and that's really quite different world opening up. I hope like it's hard to replace talking to people like face to face. But anyway, I hope we'll do that at some point. But it's good also to have this opportunity to give talk here. And this talk is for the most new stuff which I talk about here. It's based on the work with Guzman Hernandez Schifler, who is in Uruguay now, and Sharzad Zari, who is PhD student here at NYU. But it's a continuation of work which I was doing also. We started doing with Guzman, but also did with a bunch of other people. So the plan, oops, no. For some reason now it's not. Yeah, when we try, my page is not turning. So shall I try to? Yeah, I don't know what happened. Okay. Somehow now, do you see different page?
Yes.
Yes.
Okay. Somehow it's with now doesn't work with the keyboard, but works with the mouse. Okay. Let's keep fingers crossed and it will work. So this is the plan. So I will start with a review of what we called Axionic String Ansatz. And well, it's in principle, that's an ansatz which works. Well, we proposed it both for 3D and 4D glue balls in Purian mills. I'll start with 3D ones, and most part of this talk will be about 3D ones. And I'll start really just with a brief review of what was the statement, what was the prediction which we made back in that 2016 paper, and then I compare it to well, lattice data as it was at the time and as it is now, and I think this comparison looks good enough so that I will spend some time on providing derivation which we had for these ansatz. It's kind of mix of derivation and motivation. It's, as the name suggests, it's still an ansatz, so it's not really proven. And then I'll compare it to kind of closed effective strings, and I'll explain motivations to do that. And finally, I will also say a few words about what happens in 4D, although that would be very brief. So this is the plan. And well, in 3D, this Axionic String Ansatz, and I should say the name is really will be only clear when we'll talk about 4D. So in 3D, this axionic doesn't mean much, but it's kind of when one looks at the picture both in 3D and 4D, one understands the origin of the name, but still, let's use it. But for now, so the motivation for these ansatz, it comes from two different directions. One is the theoretical observation. The first is kind of theoretical observation, which is the following. Let's take a theory of a single long string, infinitely long string, and let's assume that the only degree of freedom. And now we're talking because I'm interested in at the moment in confining strings in 3D Young-Mills theory. That means it's a long string in 3 dimensions. So there is guaranteed one massless degrees of freedom there, which is position of a string, just transverse motion of a string. And because I'm in 3D, so it's a single mode. And so the state, and of course at the leading order in derivative expansion, it's the action of this mode is just Ambu-Gote action, which is controlled by non-linearized target space Poincare symmetry. And the statement is that at 3 dimensions, there exists an integrable quantization of this theory. The theory is integrable at the classical level. The Ambu-Gote theory at any number of dimensions is an integrable theory classically. And the statement is that d equals 3. There exists integrable quantization which is compatible with this target space Poincare symmetry. Just as an aside, so the same true at critical dimension at d equal 26, but at all other space-time dimensions, there is a one loop effect which leads to particle production. So d equals 3 and d equal 26 are special in that respect. And at d equals 3, well, actually it's the same at d equal 26. This quantization is corresponds to saying that this massless boson, so the way it interacts, there is a only just forward scattering, so there is no reflection, just transmission, and it's described by a phase shift of this form, where S is a Mandelstam S, which kind of in the modern language, this is a statement that, well, the theory describes TT bar deformation of a single massless boson, and kind of the statement which I'm making here is that for a single massless boson, its TT bar deformation has non-linearized ISO 1,2 symmetry. Okay, that's a theoretical observation, and kind of experimental. And for me, in this talk, experiment means lattice Monte Carlo simulation of glue dynamics. So the experimental observation is the following. So on lattice, one may look at the spectrum of excitations which live on these long strings. So one studies not really infinitely long strings, of course, but one studies strings which wound around large compact circle. So the space is a cylinder on the lattice. So one looks at the string which wound around large compact circle, and one may study spectrum of perturbations on the string for confining string. And current data doesn't show any sign of any massive modes on confining string in 3D Young mills. So it it all looks consistent so far, with a statement that the only degree of freedom which lives on the world sheet is that Goldstone mode. However, the also lattice data shows that that's not the theory which is described on the first point here, that the theory is not integrable. So let me illustrate this so that it will be kind of
sorry, Sergei, when you talk about 3D Young mills, are we talking about large n, or what value of n?
Good. I'm mostly interested in really large n limit, and that's, so maybe I should clarify here. That's what I really mean by worldsheet theory of a confining string. What I mean by that is that in the infinite n limit, if one takes really infinite n limit, that theory decouples from all the rest, and one gets really UV complete theory on the worldsheets. So, but this statement which is being made here, it's also true for essentially, n equal 2 is a bit special, but starting from n equals 3, things don't change that much when one goes from n equals 3 to real large n. Maybe there are some 10% shifts in some masses. Well, they'll show for glue balls, but this second statement, it's true both starting from, probably it's also even for n equal 2, but for sure it's true for n equals 3. Right, but what I mean when I compare these two theories, when I compare theory of confining string and theory this theory of a massless boson with TT bar d4 massless boson, there I have in mind, of course, that I work in the infinite n limit. So the theory on the worldsheet of confining string, it's 2D unitary model, which is valid up to infinite energy. Right?
Thank you.
Okay, so just to illustrate this second statement. So this is the lattice data. So as I said, what it's being measured here. So R on the left side, what's shown is on the horizontal axis is a radius of a compact circle in string units. So one looks at the string states, like states of a string which bound around this compact circle. So it's kind of stretched to large size, and these different colors show. So this is the first and 2 second excitations about the ground state. On the vertical axis, it doesn't show the energy; it shows the difference between the energy of the states and the ground state. And the ground state, well, it's kind of at large radii, just linearly grows. So there is a string. I don't show this slide here. So the first excitation kind of correspond to just KK level when you have one boson with KK momentum 1, and other with KK momentum 1 minus 1 moving towards each other. And these two levels second excitation, corresponding to second excitations, these two levels which correspond to, so that you can have either, again, two bosons, each with KK momentum 2, or you can have four bosons, two of them with KK momentum 2 and another with KK momentum -2. And so dashed line shows here the spectrum which you would get for that integrable model, well, which is kind of almost the same as you get for critical strings at level 1. So in particular, as a consequence of integrability, for on the second level, one finds the degeneracy. So this, the energy of the states is only determined by the level, but not whether it's 2-particle state and 4-particle states. And on the lattice, as is shown here, one clearly sees that there is a splitting between 2-particle and 4-particle excitations. So that's kind of the clear indication that the theory is not integrable. This can be translated into a statement about phase shift. So one can extract what's shown on this right plot here. We essentially using TBA-like techniques, we extracted from this finite volume spectrum, we extracted the corresponding phase shift, and one sees the dashed line again, that would be the phase shift corresponding to the integral theory, e to the is, to the TT bar deformation, and one can see that there are corrections to the phase shift reflecting this fact that one sees this splitting. So this is this data. Yes.
Sorry, maybe this is a tangential question, but in lattice, how does one choose to study this particular string, which is winding around the circle?
Yeah. Do you see my blackboard, by the way? If I draw something on the blackboard, do you see what I'm doing?
Far. It's a bit far.
Maybe I should stop. If I stop sharing, maybe it's.
Well, I can make the screen, your screen bigger, but let's see.
Is it better this way? It should be better now, no? Or...
Yes, but if you draw with or write with the bigger handwriting.
Okay. Yeah. So yeah, what one does, it's morally very similar to standard way how one measures everything in the lattice, measures the glueball spectrum. So on the lattice, kind of, well, the theory, of course, is cylinder, it's a torus in all directions, but let's think about it as a theory. So it lives on R2 cross S1. So let's think about one of direction being really physically compact. And that what one does, one studies the 2-point functions of operators like this. So one takes a path which goes around compact direction, and then calculate the trace of the Wilson loop or Polakov loop, which wraps around this direction, and then one studies the correlator of these two objects as a function of separation. And so this is, if one thinks about this separation between these two insertions as time, so that this correlator is given by e to minus energies of the states, which can be present on the string times this time separation. So it's important that object like this, because there is a center symmetry in this theory, and the center symmetry, strings which wound around the circle, they charge, while conventional glueballs, they're neutral. So the only states which may contribute into this correlator, they necessarily have this string which wound around the circle. And so what one does then, one, well, to determine these exponents, one looks not at the just single correlator, one creates many operators which kind of differ by, essentially one inserts some wiggles on the string. So one creates perturbations around on this Wilson loop operator by changing the shape of this trajectory, and one constructs large matrix of 2-point function, 2-point correlations between cross correlations between these objects, and from this matrix one extracts these energies, and these are the energies which are shown on the slide. Okay, let me continue. Let me get back to sharing. So any more questions about this? Oh, okay, let's just 1 second. Yeah. Okay.
So sorry. So what part of this graph indicates that there are no other states other than the massless? Is it the left end where you might have expected to see when the radius was sort of near the string length?
Well, kind of one could have seen like basically other states here. Yeah, so I'm not showing here the full spectrum, but like yeah, already on the left you see that like from Lambogota, yeah, you expand. There is this ground state energy which is not shown here, but then there is like there is first level when one expects to find single excitation corresponding to this two bosons with momentum 1 moving towards each other, and this is this violet dots, and then one expects to find two states and with momentum 2 and 4, and these are these states. So yeah, basically that all the states can be understood in this language. So there are no extra states here. But and also kind of from this phase shift one could also see. And it will be, I'll show the corresponding slides in 4D where situation is different, where there are extra excitation, and then it will be pretty clear. But basically, in terms of phase shift, these extra excitations, they would show like the resonance. So there should be a place where phase shift really goes up kind of much faster. So here it goes up with energy, but it kind of does it in a monotonic way. But yeah, the most basic level, it's on the left plot. You just all the states can be understood in terms of Lambogota excitations.
Right. And how high has this gone? So delta E times LS, has that gone to 20, 30? Or
no, so here, well, you see it's 6. The delta E is here at 6 in string units.
Right, but I was wondering whether there were other simulations which have gone higher that you're not showing us.
Let me try to think. Yeah, I don't think so.
Okay.
Well, maybe a little bit higher, but well, the data. Yeah, not. I think that's the best. That's the most sensitive channel. Yeah.
Thank you.
But to some extent, also what I will be showing later will be in some sense cross-check of this. But yeah. Okay, so these two observations combined led us to kind of morally this ansatz is kind of the statement that 3D confining strings are in some sense in the equivalence class of Lambogota. So they're in some sense deformation of that integrable theory. But it's a little bit hard to kind of make this statement sharp, and to some extent what I will be do next may be considered as an attempt to make this statement sharp and more precise, and to test this. So, and namely, but basically our logic was, but let's believe that something like that is true. So we kind of understand the theory on infinitely long string, understand qualitatively, not quantitatively. Well, part of course, yeah, I think partially one statement here is that like assumption that let's say no new states will appear as we go to high and high energies. But I'm trying to make this statement more precise here. Yeah, so let's assume this is true, and then the question is, can one say something about the spectrum of glueballs, which are in this language they're short strings? So physically, one would expect, yeah, it should be possible because glueballs expected to be there. Kind of you know everything about infinitely long string, and to get glueballs, you take infinitely long string, you cut out of it a small piece and glue it together. So it should be possible to make the statement what should be the spectrum of glueballs. But unfortunately, I don't know kind of really first principle procedure to do that. To go from the spectrum of long strings to spectrum of short strings. And so that was an attempt to do this. And what we're trying to do so far, although I'll say a few words about our attempt being more ambitious in some sense. Our most recent work is attempt to be more ambitious, but initially we tried to just predict quantum numbers. So not predict really the masses of glueballs, but just to try to understand the overall structure of the spectrum. And in 3 dimensions, quantum numbers, that means it's spin, there is charge conjugation and parity, but for states with non-zero spin, so in 3 dimensions, you get doublets, series parity invariant, so states come in the pairs of opposite parity. So really parity is only the meaningful quantum number only for spin 0 excitations. So it's for j not equal to 0, that's j and c, and for j equal to 0, it's P and C. So what we're trying to predict, we're trying kind of to get a, so these answers, what it will give us, and it gives us the prediction for the multiplicities of states with different quantum numbers. And as I said, so that's kind of, that was the prediction back then, and I later explain where it's coming from. But so the prediction was, well, first that states come labeled by levels, also in the short string spectrum. And for critical strings, again, the story is the same, that the states at the same level, they're degenerate. So here, Volchit theory is not integrable, so one doesn't expect exact degeneracy, but to some extent, yeah, the statement that this theory is a deformation of that integrable one, it's kind of the statement that one still expects to find well-pronounced groups of states which correspond to which can be labeled by level. And so this was the prediction which we had back in 2016 for first 5 levels. So these are multiplicities of states first, and this is the spin content. And I should say that starting from level 4, so there is some ambiguity in this prediction. We're not predicting all parities. So there are 2 scalars here whose parity was undetermined. So there were only predictions they should have the same parity product of this P1 and P2, but we cannot fix whether it's plus or minus. Anyway, so that was the prediction. And so as I explain later on in more detail where it's coming from, but at the moment, let me try to convince you that it's worth spending your time on explaining it, that it looks as a, like it really fits the data relatively well. So this is the data as it was in 2016. So kind of comparison to this data shouldn't be considered as a test of that prediction, because when making this prediction, we saw this data. So that was kind of input. But still, so what is shown here, now I'm talking about not long strings, I'm talking about short strings. So these are glueball states, masses of and spins of glueball states as measured from the lattice. And so this is, so coming back to this question about what group it is, so this is really SU infinity. So there's, in this work, Andreas and Sandor and Mike Tepper, they measured spectra up to SU16, I think, and they extrapolated the spectra up to SU16, and they extrapolated to infinity. But really, starting from n equals 3, n equals 4, the glueball spectra don't change that much. There may be some 10% shifts in the masses, but for our purposes, it's irrelevant. So for our purposes, we only look at the qualitative structure. But anyway, so this is really SU infinity Young Mills, and what's shown here on the horizontal axis, this is the spin, and here it's mass squared. And so, well, I color labeled the states which corresponds to different levels according to our assignment. And so here there are these first 3 levels. And they match what one finds in this table. But plus one also clearly sees several things. So first one sees it was really useful to plot it like that, namely to separate in the spin axis. If you impose all the states on top of each other, it's much harder to see like these groups corresponding to corresponding level. And part of the reason for that, there is a tendency that at each level, first of all, one finds degeneracies, splittings between states, but also one finds overall tendency that the states at the same level with smaller j, they have lower mass. But that's actually very nice, because that fits this plot here. So what I was showing here, namely what this plot shows. So if the Volchit S matrix were described by dashed line, that's e to the s. So that corresponds to integrable model. In that case, there is a degeneracy, exact degeneracy at each level. So what this plot shows that by studying long strings, one sees that the actual phase shift grows faster, which means that there is extra kind of attractive force at high energies. And now, if you think physically what these states here are, so the states at largest j, this stage which belong to leading Regge trajectory in the strings picture, So it means that kind of at large J, one may think about them as just kind of long rotating string or long rotating rod solution. And then these excited states can be obtained by adding short wavelength excitation on top of the long rotating string. So it makes sense, given that the theory has extra attraction at large momenta, as we saw for long strings. It makes sense that these excited states, they have binding energies smaller than would be that kind of horizontal prediction, which would be for e to the s phase shift. So that's, I think that's nice. So this is degeneracy. So another thing to keep in mind about this.
Hello. 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 At least I cannot.
I can't hear him either. Sergei, we can't hear you.
Not very clearly. I mean, I could hear you only a little bit. It's broken the way I'm hearing you. No, I cannot hear you. Hello.
Yeah, I also still cannot hear.
No, no, still cannot.
I just heard something.
Some very soft.
Yeah.
Yeah. Yeah, it's not like totally gone. Some crackling sound sometimes I hear, but mostly nothing. No, no, no. Zero. If you can change, switch. There is a switch microphone button in Zoom. If you can, yeah, maybe you can try doing that. If your headphone also has a separate microphone, try switching it to that.
Is it better now?
Yes.
That's clear.
Yeah, it looks like something happened to my earphones, and yeah, okay, and then they wouldn't switch also to the.
I see.
Okay, sorry for this. Yeah, let me share back where we were. Okay. Okay. So at what point you guys lost me? So
I think you knew. I mean, when I stopped hearing you, I just said hello. So
okay, good. So what I was going to say that spin determinations on the lattice are a bit tricky because, well, lattice breaks rotations. In this case, it's continuous O2 rotations to Z4. And the problem in 2 + 1 dimensions that all states are doublets. So it's very hard to really determine states, like actual spins of the states. And so what shown here, the states which are circled, these are states for which people really determined their O2 spins rather than Z4 spins. And basically the way it was done back in the time, well, so for the scalars, some of these, they just don't have a kind of pair. And that's kind of like, for instance, for this guy, for ground state, there's just a single spin 0 state. And that's how we know that it's not spin 4, because there is no corresponding doublet. But for this J = 4 state, for instance, people were looking at the kind of the structure of the state, its wave function is measured kind of from the lattice, and we're seeing whether it matches better and J = 4, continuous J = 4, or J = 0, or something else. And so for this state, it was determined that this is J = 4. Now, if one goes at higher level, then also there was a claim. So there was this J = 1 and J = 3 states. So for them, there was also claimed determination. And actually, that's something which at the time contradicted our prediction. If you look here, then at the third level, we were predicting that there should be 2J1 and 2J3. And that's not what lattice was showing. Lattice was showing that there is 1J1 and 3J3. So that was a little bit, that was a tension at the third level. But in general, there are also not enough states measured corresponding to the third level.
Sorry, Sergei, where is the level in this graph?
Well, the level is kind of, I am showing I'm coloring states which correspond to a level. So blue, so this blue, green, and lighter green, they correspond to states which, well, I think if one looks at each individual J, there is a pronounced gap. So it makes sense to
I see.
combine the states. And this matches what we have in our.
So you had 149, right? Something like that?
Yeah, so here 149, right? So this is multiplicities, because these are doublets. So yeah, so here we have 149 also.
Sorry, maybe I'm mistaken, but this blue is 1, and then the green is 3, right? 3.
Yeah, but J = 2, there are 2 states.
Oh, I see. Okay.
So that's why it's, yeah.
I see. Okay, thanks.
And so what I'm saying that, well, above, so these gray lines, gray states here, they would correspond to n = 3, and there is a tension at n = 3 because there is kind of 1J = 1 state and 3J = 3 state, while prediction was that there should be 2J = 1 and 2J = 3. And for J = 1, there were measured also higher states. So it was really clearly only one of them was showing up here. Although it wasn't known whether this is a J = 1 or J = 3, but still in this channel, there was this measurement. So that was the tension, and that was kind of, but it worked for low levels. And really, as I explain later, it's very hard to see. It really doesn't, this prediction that has 2J1 and 2J3, it's very robust. So we'll see it later. So it really didn't make much sense, this disagreement. So that was part of motivation. So I was trying to convince Mike Tapper to do more extensive simulation. And fortunately, there was a student at NYU, Peter Konke, who kind of volunteered to do that. So what we did, we performed, and by we, I really mean Peter, who was guided by Mike, and I was cheerleading. I know how to use Mathematica, but my skills don't below that and beyond that. So I was doing just cheerleading here. So what was done in this work is the goal was to really determine states, continuous spins for the glueball states. And we're doing something very, very straightforward. Namely, there are no exact Z4 rotations on the lattice, but if the lattice is sufficiently large, and here it was pretty large, then one can construct states, kind of which are roughly shown here. One can construct states which correspond to kind of approximate rotations on the lattice. So that would be rotation by, I guess, pi/8 what's shown here. And so using these states, one constructs kind of approximate multiplets, and kind of that allows to determine J really spin content of the states. It's not that different from that. The idea goes back to the paper which Mike wrote back in 2004, but it was never systematically implemented, and that was what we did here for all states. But it's rather hard numerically because we need large lattice, and some of the lattice techniques kind of for building operators cannot be used because they're not friendly to these small rotations. So that's why we couldn't go to large gauge groups. So we just did SU4 simulation. But as I said, spectrum doesn't change that much when one goes from SU4 to SU infinity. So for our purposes, that looks good enough. And so this is the result of this simulation. So first of all, so here color coding is a little bit different, but one can see, so this green states that what corresponded to n equals 3. So first, this disagreement went away. So, and later Mike understand what was causing it. So there was some misidentification of the state in the previous studies. So J equal 1 and J equals 3 for all spin states, one finds 2J1 and 2J3, and also I would say it works pretty well for the whole n equal 0, 1, 2, 3 level. So these green points here, this is what we call n equals 3, and that agrees well with, well, that agrees with, corresponds to what I have in the table before. Maybe, well, at J equals 0, it becomes all in bit ambiguous. So we kind of, the state which correspond to n equal 4 is not that far from states which correspond to n equals 3, but it's something to be expected because the multiplicity of the levels grows. So just because of that, the splittings between the states becomes larger and larger. So one expects these levels eventually to overlap, but at all other spins, there is a, I think there are well-pronounced group of states which natural to attribute to a definite level, and they all correspond to predictions which we have, but also at J equals 0, so it's not that bad. And also one should keep in mind, one should keep in mind that there's quite significant systematic uncertainties for the mass determinations here. I'm not showing them here, so one shouldn't take the spectrum too seriously in terms of mass determination, but in terms of overall structure of the states, I think it's quite accurate. So for us, it looked like a nice confirmation of the ansatz, and is a kind of good motivation to try to understand it better. So let me now spend some time to explain how actually what went into that ansatz.
So, Sergei, one question. If this were an integrable theory, what would be the values at degeneracy values at the different levels?
Well, for integrable, one expects, just like for critical strings, one expects that each level is exactly degenerate. Then in terms of m squared, there should be equal spacing between these levels, right? It's really critical string spectrum than it would be, but it's not d equals 26, it's d equals 3. I should say, I don't like, in the beginning I said that there is integrable theory for infinitely long string, but I don't think this theory exists as a theory of short strings. I'll say a few more words about that later. But kind of what I'm saying here, I'm almost saying just comparing to expectation to the case when we know the theory exists, which is d equal 26. But maybe it sounds a little bit obscure what I just said. I'll explain this point later. It will be more clear, hopefully. Okay, so that looks for us as a encouraging enough agreement, as I said, to spend more time understanding why this ansatz works and how it works. So let me spend also some of your time then to first say what we did to come up with this ansatz. And it was, to a large extent, it's inspired by what we know about critical strings at d equal 26. but also by just some common sense. So the first assumption was, well, this is this tensor square structure, and I think that's really kind of common sense. It's just what you so what you mean by one-dimensional object with only massless excitations on the world sheet. So we said there should be well, there is the structure, overall structure of the Hilbert space should be such that there are left moving states, right moving states, and then the total momentum for closed string, which doesn't wind around large circle, but short closed string, the total KK momentum should be 0. That's level matching conditioning string theory, but it's really just a statement that the translation along the world sheet is a gauge generator. It's a that's not a global symmetry, that's a gauge symmetry. It's a diffeomorphism of the world sheet. So the total charge should be equal to 0. So the total left moving KK momentum should be equal to the total right moving KK momentum. And that's where level matching condition comes in. So we made these ansatz. So that the Hilbert state should have this overall structure, and already here, so there is an input here. It's not completely general. If there were extra massive state on the world sheet, then this ansatz doesn't work. Then you would have additional states corresponding to the fact that you may put a state when you have massive particle on the world sheet, then you may add it to the world sheet with 0 momentum. And the structure would be different. So here there is an input that we're assuming that there are no massive states on the world sheet. And furthermore, the charge conjugation, it acts by changing the orientation on the world sheet, right? Charge conjugation acts on the gluon field by changing the sign. So it acts by inversing the direction on Wilson line. So it acts by exchanging left movers and right movers moving states. And on the other hand, parity, we assumed it acts just separately on left movers and right movers, and we don't know how to assign it. So we just left it free. And so already this assumption, which is presented on the previous slide, it's already I don't know why it's sorry. It's already quite restrictive. Because one gets in this multiplication table, so it's kind of just O2 multiplying O2 representations. So what can come out from multiplying these ingredients? So first of all, one gets predictions that at each level the multiplicity should be a square of an integer. And furthermore, if you look at this multiplication table, you see that the only place where you can get odd spin states, it's on the last line. If you take kind of states of different spin from left mover sector and right mover sector and add them together, but then you have J1 cross J2, but also you have J1 cross J1, J2 cross J1, sorry. And when you look at the content, then you find that you predict that odd spin states, they come in the pairs of opposite C parity. And that's what wasn't true for this J equal 1 and J equal 3 states in the old lattice data. So that's why I'm saying this sounds to me like really very basic prediction of the string picture for glueballs, that odd spin states should come in the parity in the pairs of opposite C parity. That's why we're kind of so confident that we're not worried about that discrepancy. We saw it more as an opportunity to see that what we're doing is correct. Okay, so well, that's part of the story. Of course, that's already somewhat restrictive, but it doesn't yet give us prediction for actual content of each of the levels. And to get that prediction, we did the following. So we said, and that's really where we were inspired by what happens for critical strings. So we said for critical strings, we know that this left mover and right mover Hilbert space is the same as Hilbert space of open strings. And yeah, I don't know how to motivate that like in the basic physics level. It's just here we're using input from what we know about critical strings. And then the Hilbert space of open strings at large J, that can be determined doing perturbation theory around classical rotating rod solution. So that's something we already said, right? So there's a state on the leading Regge trajectory, which described by this solution. And then one may consider small perturbations around this solution, construct this Hilbert space at large J. But let me go in some details of what we're doing, because actually the new part will be about going into detail of this calculation. So let me go through some details of this. By the way, you guys hear me, right? Just to make sure, because there were no questions for a while.
We hear.
Yeah.
Yes.
Okay, good. Because one is getting worried in the Zoom talks and you're disconnected and nobody hearing. Okay, so first of all, in principle, we work in non-critical strings here, so it's not d equal 26, d equals 3. So the way to do it at the effective string theory level, and here we talk about what we're doing. We're planning to take this long rotating string solution and do perturbation theory around it. So that's a perturbative calculation, in a sense it's the curvature of string is small. So that can be done using this kind of Palczynski-Strominger version of the Polakov formalism. Namely, one starts with Polakov action, but one adds to Polakov action the extra term, which is the basically it's built using it's a composite operator built using fields which live on the Volt sheet, whose Weyl transformation cancels the anomaly. And it enters at the end of the day, it enters in the higher order in derivative momentum expansion. But our purpose is for the purpose of calculating the spectrum. Really, we can just we can neglect this because, as I said, that's high order in derivative expansion effect. So we don't need that. But conceptually, it is there. If one wants to calculate or go in more precisely, then one needs to include this effect. So we work really, but we essentially work at 3 levels. So we can just use Polakov action. So one starts with Polakov action, and it turns out that for purposes of what we're doing here, it's more convenient to use first order formalism. Well, it kind of gives more clear phase space structure of the theory. So we rewrite it in the first order formalism, where it's usually one introduces pi mu's, which are kind of on shell become canonically conjugate momenta to x mu, and so then one clearly sees that it's just a constraint free theory where Virasoro constraints they generate gauge transformations, and so this is a canonical symplectic form. These are Virasoro constraints, and we go to static gauge, which is kind of
the H's in the previous transparency. You're going to gauge fix them.
No, so far I didn't gauge fix. So far there's no H here. So these are the components of Polakov metric, but here they play the role of Lagrange multipliers. In the first order formalism, they are Lagrange multipliers for Virasoro constraints, right?
Yes.
And so then what we do, we gauge fix axis. So so this is a kind of formalism which allows to do, for instance, one can use it also as a version of light cone gauge, which kind of usually in the standard formalism, light cone gauge, you first fix H to be conformally flat, and then you do additional kind of on-shell gauge fixing to go to light cone gauge. But in this formalism, one may do it differently. One may kind of fix in some sense light cone gauge condition from the get-go, and then H comes out from solving the equation for Lagrange multipliers. And so the same, so we do the same, but with a slightly different gauge. So instead of light cone gauge, we use a gauge which is more suitable for the study of this long rotating rod solutions, which is static gauge. So one fixes x0 to be proportional to tau, and one fixes pi 0 to be just a function of tau. And this function on shell, it will become the target space energy of a string. So on shell, it will be E of tau will be constant, but off shell, it's in principle, it's a function of tau. So these are our gauge fixing condition. And so but now if one writes equation for x0 and pi 0, then these equations combined with Weyl symmetry, which is still there, which is another gauge symmetry, which is present here, that fix H to be flat. So in this formalism, it's kind of goes in the opposite order. So the flatness, like induced metric being equal to Polyakov metric equal to Minkowski metric, it just follows from equations of motion. So after one does that, well, one is left with x and p. So these are complex. This x here is a complex combination x1 plus ix2, and pi is also pi1 plus ip2. So one left with this transverse degrees of freedom. So there is a tower of oscillators, of complex oscillators. But in addition, there are still Virasoro constraints, which now become well, we already fixed the gauge, so they just become, I was confused, like either first order or second, like not the generators of gauge transformation, but one can just solve them away and get the physical Hilbert space. So one by solving the constraints, solving the constraints removes half of the oscillator, so one left just with a single real oscillator as expected, and so one gets the physical phase space, which describes, so there is a position of a string and the conjugate momentum. Then there is a kind of this Goldstone mode, because I'm expanding around rotating string solution. So there is a Goldstone mode, which is the phase with the phase here, and it's a variable which is canonically conjugate to the angular momentum of the string. And then there is a bunch of oscillator modes, but these oscillator modes, they start from kind of the frequency equal to 2. Because the frequency equal to 1, it's kind of, it corresponds to moving, to changing the J, so that got removed. It's kind of, in some sense, you might think about it as a kind of Goldstone boson which got eaten. Anyway, so one gets the structure. In particular, the J, the angular momentum, is canonically conjugate to this phase, which is 2 pi periodic, and that leads to the statement that J is integer quantized, which is slightly non-trivial statement, and that's kind of gets me back to this comment which I was making, that I don't think that integrable theory really exists in the short string sector. Namely, a few years ago, there was a paper by Mezinchenko and Townsend who pointed out the following. So if one does light cone quantization, not what we're doing here, but if one does light cone quantization of bosonic strings or superstrings, then there is an anomalous commutator, usually, which is G plus I and G plus J, and that's the Poincare anomaly, and which vanishes at D equals 26. But of course, it also vanishes at D equals 3 kinematically, because I is always equal to J there. So they thought, oh, there is no anomaly in D equals 3. Let's quantize the theory using light cone in D equals 3. And one does that, but when one gets using light cone quantization, that then necessarily, if one calculates helicities of the states, one gets irrational anyons in the spectrum. And kind of, well, they said it's interesting, but I think it's interesting, but I think it's indications that really light cone quantization, it's also anomalous in D equals 3. So it's more like, I think it's similar to chiral anomaly. Chiral anomaly, when you have n, like number of colors larger than 2, then it shows up in the local commutator of currents. But when you go in equal 2, it still shows up as a global anomaly. And the fact that here we started with a theory which was invariant under just Poincare group, and as a result of quantization arrived at anyons, I think that's indications that really this quantization is anomalous. It changed the group of the theory. So for me, it's indication that, well, that theory doesn't exist really in D equals 3 as well. However, this quantization which we are doing here around long string, it doesn't have this property. It correctly gives quantization, integer quantization of the angular momentum as a consequence of the delta C periodicity.
Sorry, if you just took the 26-dimensional string and restricted to the sector with all oscillators except 3 sort of in the vacuum, would you get more or less the same spectrum?
Well, I'll show you. Yeah, good. I'll show that my next slide roughly shows more or less that comparison. Not, yeah, it's slightly different, but probably it's more or less the same. Yeah, okay. So, good. So what's shown here, this is kind of what one gets from, yeah, okay. Then the next step which we made, which was really kind of very brave and not motivated at all, apart from the fact that it kind of worked for the lattice data at the time, and it seems to be working with lattice data now. We said, so, okay, this calculation gives us the structure of the Hilbert space at infinite J, at very large J. So let's just take the same answer for open strings. Let's just boldly take it for all J, all the way down J equal to 0. And this is kind of what's shown here. And yeah, actually, the more I think about it, at the time, it looked like quite natural for us. The more I think about it, the more puzzled I am why this would work. But it seems to work, as I was showing you. And well, kind of maybe the motivation, and one way to justify it, that again, one thinks that what we see here is some deformation of something in integrable theory. Then in integrable series, it's often the case that semiclassic produces the correct answer. And here we're talking just about discrete data like spectrum of the state. So maybe that's what kind of explains it. Okay, so this is a comparison kind of what Shiraz was asking about. So what it's slightly different. What we do here is the following, but maybe it's more or less what you said. So what we take result of light cone quantization of bosonic string, which at d equals 26, of course, that would be the correct answer. And this, but then we analytically continue its helicity content from d equal 26 to d equals 3. And it's known that at all levels, apart from level 1, so the states which you get at any number of dimensions, they actually come in the representations of the correct little group. It's only, and that's kind of the fact that all the numbers here positive. So the fact that one has -1 here is a statement that, well, it's the usual the usual statement that one needs in the conventional strings, one needs this level to be. It's not a representation of massive little group in d dimensions. It's 1 dimension less, which is massless little group. So this should be massless state, and that's what this -1 indicates. And so what's shown here, these red entries, that's where this analytic continuation, where it agrees with what we found. So, which makes sense. So in the vicinity, the two prescriptions agree. If you want, it's a cross-check of kind of our calculation. But for sufficiently highly excited states, we predict more states. So this analytic continuation underpredicts states compared to what we have. So for these black entries on these two plots, they're different. And in particular, they're very different in the first level. But yes, there is no surprise here. One doesn't expect different prescription to agree away from the regime of validity of effective string theory. So the surprise, as I said, is that one takes our prediction and then makes it, uses an input for in the tensor square, that one gets a result which agrees, we seem to agree with existing lattice data up to for many glueball states already. So that's the surprising part. Okay, yeah, I'm running out of time, but how much time I have, because we had all these interruptions.
Yeah, so usually we are flexible with time, so don't worry too much about it.
Okay, good. Okay, but also I won't take that much time. I know it's also getting late for you guys, but thanks. So one natural question to ask is,
sorry, Sergei. So the difference between your prediction and this analytic continuation you were talking about is sort of like the difference between the semi-classical answer and the exact answer in 26 dimensions. Is that right?
26 dimension, it's difference about semi-classical answer and exact answer.
Right.
And there it's pretty clear where it's coming from, because in 26 dimension, the states as a leading Regge trajectory, they also can be thought of by acting with a dagger 1 on the vacuum state, on the tachyon, certain number of times, right? And this disagreement comes at the point when when excitation is equal to J, when acting with new states, you're kind of exhausting this condensate which you have on the classical Regge trajectory.
Okay, yes, thank you. Yeah. And then your suggestion is actually the semi-classical answer is better than the the continuation of the actual answer, 26 dimensions.
Well, for confining strings, it seems to be better. Well, it's clearly better for like at this level. So we want to add something to this exact answer for sure. And I think the way to think about it, it's really the problem of confining strings is kind of is a problem of Higgs mechanism for the string version of the Higgs mechanism, right? Because with a major problem which we have that we need to find a way to get rid of tachyon for bosonic strings. But why is tachyon is there? Well, because there is massless state at the first level, and so somehow one needs to lift that massless state, and then one can also lift tachyon. So somehow one need to add something, and as usual, kind of to get a mass to particles of non-zero spin, one needs to add something to there. And here one needs to do it consistently at each level. So I think about this whole problem as really somehow one needs to find a prescription how to kind of standard critical strings, add something such that one would be able to lift the whole tower. So one is, yeah, I'm not concerned that by the fact that I'm adding extra things. We know that one needs to add extra things. Still, it is surprising that the semi-classical prediction seems to work. So
yeah, thank you very much.
Well, then next step, at least one thing which one would like to do, because one would like to test it further to higher levels. At some point, it becomes problematic to the fact that I said so, because you have high and high multiplicities, so one expects this level to overlap more and more. I should say in the existing lattice data, even at n equal 4, so essentially we have quite a few states there, and at all values of j where there is a well separation between levels, it looks like there is an agreement with the prediction which we have for n equal 4. So it does look also quite good further, but more work needs to be done for that. But also, it would be nice to learn how to calculate the splittings perturbatively. I clearly see here some pattern. So it would be nice to do some calculations, more quantitative about splittings. And well, it looks like, and that's the main question which we're trying to address now. And what I'm presenting now is the first step towards doing this. But at least for some of the states, it should be possible to do using effective string theory. So, namely, instead of modeling, going through these open strings and taking tensor square, the states on the leading Regge trajectory can also be described just really closed rotating rod solutions, right? And for large J, directly in the closed string theory level. And for large J, again, there should be good approximation, and then one can start studying fluctuations around this closed rotating rod, and that way, by studying that fluctuations, one can one should be able to calculate also splittings between low line states close to leading Regge trajectory. So that's what we want to do. So to be honest, back like in 2016, I didn't expect. I thought that it would produce more or less that it's more or less the same equivalent to what we are doing at the level of open strings. But as we'll see now, actually it is not, and that's a bit of a surprise. But yeah, so we're doing something very similar to open strings, right? So just to summarize what we did to open strings, just overall picture. So we considered long with this rotating rod solution. Then after fixing the static gauge, one has this complex X of this type with this complex oscillator. And then one imposes Virasoro constraint, which removes half of the oscillators. It removes some extra state in the n equal 1 sector. And as a result, one gets also delta is a periodic variable, and one gets that J takes integer values. And one gets a tower of n larger than 1 oscillators. So that's that was the picture for open strings. So we're doing the same for closed strings. So for closed strings, everything looks very similar. So as usual, things are getting doubled. So we got now 2 towers of complex oscillators. One imposes Virasoro constraints, And now, because there is a residual gauge symmetry after one fixes a static gauge, which wasn't present for open strings, which is shifting sigma by constant, which is not allowed for open strings. Here it's a periodic, so one can do the shift. So by making use of that symmetry, that removes delta rho and B, this modes and equal sector, is it removes half of the oscillators. So it looks all very similar to what happens for open strings. Again, delta is a periodic variable, that hence J takes integer values. And at J, we have 2 towers of n larger than 1 oscillators. Well, there is something extra which happens for closed strings. Namely, even after all this has been done, there is still a residual sigma, like shift by sigma by pi, which doesn't affect this delta rho in B modes. So that symmetry is still not fixed. So there is this Z2 transformation, but it changes delta, and it flips the sign of some of the oscillators. So what one needs to do now, one needs also to project two states which are even under this Z2 transformation, because it's a residual discrete symmetry which is present here, and that for instance explains why there are only even J states on the leading Regge trajectory directly in closed string language. The reason back in 2016 we went to the tensor square that I didn't know at the time how to explain. So it's just empirical fact on leading Regge trajectory there are only even J states appear. From open string picture it's clear why it is, because you take a tensor square and you get to J. From closed string picture it wasn't clear to me, and it has to do with this residual Z2 gauge symmetry, which now projects states differently at even and odd J. So after one does this projection, then one can say the same what we did for open strings. Let's try to do this, to play the same game. So we got some spectrum at large J. Let's compare it to what we had for open strings, and let's compare it to the actual spectrum. So let's push this semi-classics all the way. And well, somewhat surprisingly to me, but a posteriori maybe not that surprisingly, one finds that this prescription gives different answer from the previous open string calculation. It overpredicts states even further, and it's a clear conflict with data. For instance, predicts well, already at n equal 0, 1, 2, it predicts odd spin states for 2 odd spin states at the second level, which are not present. It predicts 5 scalars here instead of 3. So first of all, it's nice illustration that kind of not everything goes. So one can do something which wouldn't fit in the observed spectrum. Well, it kind of illustrates, I think, that it is somewhat surprising that what we did for the previous procedure worked. So this procedure gives different answer, and it further over predicts states. But on the other hand, again, these red entries here, so that's a consistency check. So in the vicinity, in the large enough vicinity of the leading Regge trajectories, the two prescriptions agree, and that's where one can now start doing effective string theory calculation. One can start calculating the splittings between the states. That's kind of our plan for the future, to go ahead with those calculations for the states which are under control here. Okay, that's the end of 3D story. So I have a couple of more slides to illustrate, but it will be very fast for 4D. But are there any questions about situations in 3D? No, okay. So yeah, let me I'll briefly conclude. So, but let's just describe situation in 4D. So 4D ansatz, well, inspired again by 2 observations, but I changed the order here because kind of here the experimental one is more is driving the game. Namely, lattice data for confining string in, sorry, it should have been 4D. It's in 4D Young Mills shows a massive pseudoscalar state on the volt sheet. So there is a massive state which is observed, and it's a pseudoscalar rather than scalar, which we call volt sheet axion. But really, one may think about, I think it's a gluon. It's basically when you have, if you think about long string, you can insert like in the lattice language, you can deform the string in the transferred in the longitudinal direction. It's sort of like a placket attached to string that corresponds to Goldstone boson. But one can also insert the placket in the transverse plane to the string. Like if this is z direction, one can insert Fij inside the Wilson line, and that's a gluon insertion, and that corresponds to pseudoscalar excitation, and that's kind of what one is finding. And there is analog of this theoretical observation also in 4 dimensions. Namely, at d equal 4, there is an integrable quantization of an Ambu-Gotha action plus a massless axion, massless pseudoscalar, which is compatible with ISO 1,3 symmetry. And again, it's CT bar deformation of this whole theory. So if you just had 2 massless bosons and you do CT bar deformations, that's incompatible with ISO 1,3 symmetry. But if you add massless pseudoscalar, then that theory again has non-linearized Poincare symmetry. So kind of the meta content which we find in 4D, namely these 2 bosons and this additional axion, is the same as an integrable theory, but it is massive. This additional particle is massive, so again, it can be only deformation of this of the integrable theory. And so this is what I promised you in the beginning. This is a slide shows how one sees the presence of extra massive states. So here again, these are for long winding strings, states corresponding to first level. So it's one particle with momentum 1, another particle with momentum 1. For an Ambu-Gotha, one expects there should be, so these are different channels. Now we're in d equal 4, so there's O2 symmetry. So we have states which are green line correspond to tensor, spin 2 under O2, blue that's scalar, and red is pseudoscalar channel. And the critical strings would predict, or just Ambu-Gotha would predict that everything, all states are degenerate and belong to the dashed line. And one see, first of all, there is very large splittings here, but also there is, and well beyond what one expects from kind of perturbative corrections, but also this state here, this red state, it has a property that its gap, and what that was shown on the vertical axis, its gap roughly constant as a function of radius. So that does look like just a massive particle added on the volt sheet. Well, yeah, I don't have, but there is a similar plot with a phase shift. So one sees the state as really the resonance in the phase shift, rather sharp resonance. Sorry, yeah. So then one can follow the same logic, and well, no, the logic was different, but one can try to play the same game. So one can try. Let's start first pretending the state is not there, and said we just have Ambu-Gotha, and nothing else. Then what do we expect? Then similar how we did in d equals 3. So here one expects n equals 0, 0 plus plus, and n equals 1, one expects 0 plus 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 vector plus spin 2 glueball. We know that's probably not the correct answer, but that's nevertheless look at the data. So this is the data which is much less complete. So this is the data for d equals 4 glueballs. So first of all, well, there is a ground state here. This is 0 plus plus. That's good. But then, well, it looks like, honestly, it looks like quite a bit of a mess. Well, but if one looks at n equals 1, so there are these 3 states, this blue triangle here, this square, and this 2 plus plus. So these 3 states, well, they're not terribly degenerate, but they're relatively close to each other. At least this is 0 plus plus, 1 plus minus, and 2 plus plus. So these states, they look like they can match this Ambu-Gotha prediction. But then there is this additional state, which is 0 minus plus. And that's one is very hard to get from doing any tensor squaring thing. But on the other hand, this 0 minus plus state, it has exactly the quantum numbers. If I started from 0 plus plus and added this massive axion which I have in this theory, that would be exactly this 0 minus plus state. So it's natural to interpret this kind of what happens here, that these 3 states, this is first Ambu-Gotha level, and this state is there because of the massive axion. Of course, it's very hard at j equal to 0. It's very hard to play this game because there's no perturbative description of that. But so what we are doing now, that's a work in progress. So when one goes to kind of j equal higher j, for instance, well, j equal 2, well, it's not terribly high, but one can at least at large j, one can do, so there is also similar state here. There is 0 minus plus state, and this 0 minus plus state is natural to interpret as adding an axion, again, massive axion on top of the closed rotating string. And so what we're calculating now, we're calculating whether the state is indeed agrees with whether it agrees with this interpretation. But yeah, so this is work in progress. I don't have much more to say about that. So clearly, one needs better data. And also situation here is more complicated. There is kind of, it's hard to write. So here, at least at the moment, what we can do this closed effective string approach. We can namely do perturbation serialized closed effective string. We don't know, there is no analog of this tensor squaring because it's not clear how to include perturbation, like interactions there, and at what stage to add axion, to add it before the squaring or after the squaring. So it's a little bit confusing.
Sorry, Sergei, could you say again which was the j equals 0 state that you have attributed to the
this square, this 0 minus plus state. So it's 0.
Right. So its mass is something like 5 times string mass, because mass square is 25.
Yeah, this gap, I think the gap between the, well, it's mass, something like 5 times mass, but maybe more relevant quantity is the gap between this state and the 0 plus plus state. Well, I'm not sure. Here, I really don't know how to calculate. Well, I think at the moment we don't have a tool to calculate anything here. At large J, the way one calculates it, what I said, we take closed rotating solution, add a massive particle on top of that. But it's the calculation. It's not as simple as to say that you shift the energy of the state by the mass, because what happens is the following. So you have this closed rotating string, which is long string, it rotates, and if you have a massive particle there, what it does, it gets, because there is a kind of, everything is rotating, so it's there is a centrifugal force which pushes this particle towards the end point of a string. And so one should really, it's a kind of, there is some material-like potential when there is some Schrodinger problem to solve. It's not just that the mass is being added, because string is not straight string. It rotates, so there is extra dynamic. So it's more like adding some renormalization of the endpoint mass of the string. It more looks like that way. And actually, from that viewpoint, one expects to find not a single state, but a pair of states. So you see there is this 0 minus plus, but also there is this 0 plus plus state. And one expects, because there are 2 endpoints, so one expect to find 2 relatively degenerate states, at least for long strings, 2 rather close states, which correspond to kind of even and odd combination when the particle leaves at 2 endpoints symmetric way. And so most likely, actually, after one accounts for that, that maybe the level structure here will be more convincing. If it turns out, which looks very plausible to me, that both the states, both at j equal 2, both square one and the triangle one, they both come from these extra massive modes, then it would be much less problematic to say, well, this is 0 level and this is the first level of Nambu-Gotha, and there is really a gap to higher line states, because these extra states which we're finding here, it's really more like contamination from the extra massive particle which is present.
So I was wondering whether there might be in this case an infinite number of extra massive particles. The next one's at 10, let's say, and you don't see it because it's not gone high enough. Is that unreasonable?
Yeah, I don't.
In general, it's surprising you've got so few degrees of freedom, right? There's a thick string. It should be possible to wiggle it in many ways. That's not just its center of mass motion. Each of those should have some degree of freedom. So already the fact that you had no massive particles in 3 dimensions, to me, seems quite surprising.
Well, no, but these wiggles, these are just geometric deformations of a string.
No,
right?
no, I don't mean wiggles of the shape of the string. I mean wiggles of the thickness.
You mean, right, but that's kind of the state. Yeah, this is in some sense fundamental string, right? That it's an n to infinity limit. It becomes
maybe it's a. I mean, in ADS-CFT, it would be a fundamental, in those strange ADS-CFT models, it would be a fundamental string, but in 10 dimensions.
Right. No. Yeah. So it's definitely in conflict with like ADS-CFT picture in the gravitational regime, right? Because there, even the fact that we find in pseudoscalar there, right? Because I think the zeroth order prediction of holography in the gravitational regime is that there should be a scalar mode, which is like the Liouville-like mode on the string.
Right.
And here we don't find anything like that at d equals 3.
Right.
We don't find anything like that at d equals 4, and instead we find the pseudoscalar. So yeah, I think for me it's a clear indication. I don't think it's a problem for holography. It's a problem for holography in the Sugra regime.
Right.
The curve is so strong here that that geometric picture is really lost, and one gets degrees of freedom and not captured by the naive.
Right. But if you look at this thing, the string will have a certain the flux tube will have a certain thickness, right?
Right.
Now you would imagine that it should be possible to do something to shrink the thickness by half, to push it and let that oscillate. And somehow in 3 dimensions, you're saying that's not really possible, right?
Yeah, right. Yeah.
Isn't that strange? I mean, that's amazing if it's true, right?
Well, I think and the way I interpret it is that these companion strings are much closer to being like elementary objects, much closer to be fundamental strings.
Which means you can't push them, right? You can't.
Right.
Yeah. Right.
And
I mean, that's totally amazing, right? I mean, you wouldn't have thought so, right? At least I wouldn't have thought so. Right? You might. Yeah. Okay.
Well, but the remnant of this fact that there is this thickness is that the theory, because for instance, if I take St bar deform theory, right, that it's not described by UV fixed points.
Right.
So there is the thickness. So the bullshit theory is,
right.
I think.
So the thickness is sort of like giving you a cutoff, but it's not giving you a dynamical mode.
Right. It's given non-locality. Yeah. That the theory is really gravitational on the bullshit. It's not a quantum field theory in the UV.
Yeah. But knowing nothing, I would have expected it to do both, cut off the theory, but also to wiggle. And you're saying it does one, but not the other, which is totally amazing and fantastic.
Yeah, I think that's what makes this whole story very interesting.
Yeah. Okay. Thank you.
What we did with glueballs, right? So that's a cross-check of that, because you were asking me up to what energy on the string we see that there are no extra massive states, but also if we have these extra massive states, like also as this picture illustrates, you expect to see them in the spectrum of glueballs. And the exercise which we're doing in 3D, the spectrum of glueballs, there is just no room for extra states. So one should really, well, at least if they're there, they're pushed pretty high. So the lower lines, like many levels of glueballs, they just can be interpreted just excitations of Nambu-Goto string and no massive modes.
Thank you very much.
Yeah. But yeah, you are absolutely right. I think that's maybe the most interesting aspect of this story, right? So this mass scale, the thickness, introduces non-locality but doesn't introduce new degrees of freedom, right? So any more questions?
So have you finished the talk, Sergei?
Yeah, that's it.
Oh, let's all unmute and applaud. Thank you, Sergei, for a wonderful talk. Let's see if there are more questions.
Is there any way you can check another regime, which is somehow like, is there any way to check, let's say, the Hagedorn spectrum or something like that against one of your predictions?
Well, at least in d equals 3, one can take that ansatz, because we have ansatz for the whole spectrum, and one can calculate the density of states. Yeah, and of course, one does get Hagedorn, right? Because it's
right. But is there some way to check? Very ignorant question, but is there some way on the lattice just to directly compute the Hagedorn temperature?
Well, from it's not directly Hagedorn temperature, but when you look at the long strings, right, then there is this a center symmetry transition, right? So when you take the size of the circle sufficiently small, then center symmetry gets broken, which can be interpreted as, in the string theory language, is that, well, there's a closed string tachyon now, right? So, and that.
So it's a string that you're forcing to wind, and then it becomes tachyonic.
Right. Yes. Right. But it's an azimuth. It's closely related to this.
Right. Can you compare when that happens to your predictions? The radius at which that happens to your predictions?
Well, it happens at very small radius, so there in some so we don't have prediction for that.
Okay. Yes.
But it happens. But also it's true that the ground state energy it's very close to just doing ground state energy of TT bar deformed series. So in that sense, it's almost there. So there are corrections which actually Mike already sees. There are some 1/7 corrections. So it's not exactly that, but it is very close to just doing TT bar, comparing to what you get from TT bar deformation. Yeah.
Okay. Right. I was hoping to see that if there were additional oscillators that would show up at high enough energies. I was hoping to get a cross check on that somehow. But you say, yeah.
Well, for sure, one should push these measurements and to look for and also the glueball spectrum.
Okay.
But it's already pushed quite
yeah,
far.
Yeah, no, it's amazing. It's amazing how well it's working. It's totally amazing. Could I ask one more, probably very stupid question? You said that if you take two scalars and TT bar deform along with a third scalar, you get something with 4-dimensional Lorentz invariance. Could you, I'm sorry, this is just my ignorance, I should know this, but could you explain roughly why that happens? Or is there some intuition for expecting something like this?
Well, actually, yeah, do you see my blackboard?
Yes. Please write as big as possible.
So first of all, what I said to the scalar. But the same is true for scalar. Yeah, so if you start with, do you see it writing here?
Okay, I need to.
You don't see it?
I can see it. Yes.
Yeah, I can see it too.
Also, I don't know. Does it help when I quit sharing?
It's fine. I have you on full screen, so.
So technically, what one does, one starts with Nambu Gotter for long string, right? So in D dimensions. So this is Nambu Gotter theory. Then for Nambu Gotter theory, so at 3-level, it's integrable. At one loop order, one finds that there is a calculable, because there is no one loop counter term in this series, and at one loop order, one finds that there is a particle production from diagrams like this, and which is proportional to d minus 26. At 3 dimensions, it vanishes for some kinematical reason, but in general number dimension proportional to d minus 26. So there is this this particle production, and then one might ask, okay, it's an anomaly, meaning that we're trying to quantize theory consistently with Poincare invariance, and there is classical integrability, but at d not equal 26, there is a clash between the two. So one may ask question, as usual with anomaly, what one can add? One need to add some massless degrees of freedom. What one can add to cancel that anomaly? And one may add, for instance, the simplest thing to add, let's add one more scalar degree of freedom, which may add to keep integrability at the classical level. It's natural to add it inside like an extra dimension as a leading order inside here. Now, if it's scalar, then the lowest interaction which one may write interaction like this, where R is a metric, the curvature of the induced metric with some coefficient. And then, in addition to this diagram, one gets a diagram where you just exchange kind of the scalar, 3-level diagram from the exchange of scalar, and then it turns out one can find this coefficient in such a way that it cancels this anomaly. And then one can show that we have perturbative proof that just order by order in perturbation series, or the moment you cancel it at one loop order, at higher loop order, there is no abstraction. There is always you can choose counter terms in such a way that particle production is absent. And so what I described for you is a very complicated way to describe something very well known, namely the linear dilaton theory. Just we derived it here in a completely different way, starting from this question about integrability, but it's really the same. It's just very complicated way. In that case, it's a very complicated way.
And the slope of the dilaton is chosen to make the whole thing c equals 0, c equals 26.
Well, no, it's chosen in such a way. Well, here it's fixed. It's related to this coefficient.
Yes.
So it's chosen by requiring that kind of this coefficient appears in this diagram. So here it's chosen from requiring that this diagram cancels particle production from one loop effect.
Yes, but in the end, you get a critical theory in the end, right?
Yeah, it agrees with what we get from, but here we never have kind of violent variants. We're not using, work in a different language. Kind of, yeah, I think it would be good to understand a better relation between the two. But anyway, so this is how integrability logic, how it gives linear dilaton. But then the observation is, so let's say this is not a scalar, but let's say it's a pseudo-scalar. And then in 4 dimensions, there is another operator, let me call it A. And there is another operator, which one may write, which very similar properties. Namely, the property of this operator was that this dilaton it was shift invariant because R is a topological density. So in 4 dimensions, there is another topological density which can be written through it's basically KK tilde, which is an extrinsic curvature. So this topological invariant, it would calculate the self-intersection number of a string bullshit in 4 dimensions, which is a topological invariant for two surfaces embedded in 4 dimensions. So there is this term which one may write, which is specific to 4 dimensions, again with some coefficients, and then one may repeat all the same logic which led to linear dilaton theory. At this level, one may repeat again. One may use this coupling to cancel particle production, and then there is no abstraction at higher order in loop expansion. So that one can push this theory to get a Poincare invariance theory. So from the point of view of kind of this integrability question, these two theories they look very similar. There are 2 different answers to the same question. What is the simplest way to fix? What are the simplest ways to fix? Remove this particle production compatible with Poincare symmetry. Of course, in the conventional language, they look very different because we don't have a simple description for this one. Because here I have this extrinsic curvature. So there is no kind of useful Polakov rewriting of the theory, which will reduce it to some bullshit CFT. So, and that's the problem. But on the other hand, it matches very nicely different. So this picture, there are these 2 different ways to restore integrability, matches very nicely the recent study, which was done by Pedro Vera with friends, where they were using S-matrix bootstrap for flux tubes. And what they found there, that they found that there are there is a loud region as usual in these bootstrap studies, and there are 2 borders of this region. And one border, close to that boundary, one finds a rather narrow, light scalar resonance. So that's kind of looks like holographic theory or conventional critical string theory, right? So with this dilaton present there. So that's dilaton, that's what one expects in holographic models. But there is another boundary which they find. So on the second boundary, there one finds the light, narrow pseudoscalar resonance. And that's kind of the series which seem to correspond to a really QCD regime. And actually, surprisingly, what they find from Bootstrap, the parameters of that resonance. One thing I didn't tell for you, which I think is actually quite interesting. For us, initially, that was one motivation. So again, here from this integrability considerations, one determines the coupling constant here for the dilaton, for the axion. And that's something which can be also measured from the lattice. That's something which we did determine from the lattice. It gives a kind of decay width of the axion. And so from lattice, like within current uncertainties, within error bars, which is at the level of 10% to be conservative, one finds from the lattice, one finds the value, even though axion is massive, this value of the width agrees with the value of this coupling constant to be required by integrability. And that's also what Pedro finds close to the boundary of that region where you have light axion. That's exactly what he finds, that particle there has parameters which again agree with integrability and with the lattice. So
sorry, one more quick. Sorry for asking so much. In the case that you had this extra direction with the linear dilaton, there you would have a new continuum associated with motion in this direction, right?
Yes.
So that would be very, very different from a QCD-like spectrum.
Right.
Here you don't have such a continuum, right?
Well, because it's a mass.
Massive,
yeah, it's a
yes. Right.
Yes.
Okay, thank you. Yes. Yeah, that's it. Thank you.
But there also one can, because series is not integrable. Also there one can imagine series where the dilaton gets a mass, kind of some deformation. So it won't be again conventional critical string, but one expects it. In holographic models, it's not exactly massless.
Okay, thank you.
That aspect of it is not special. So yeah, sorry, it wasn't very direct answer and not very kind of because
No, it's a great answer. Thank you so much.
Okay. Are there any more questions? If not, let's thank Sergei again for a wonderful talk.
Thank you.
Thank you so much, Sergei.
Thanks so much.
Yeah, this is very interesting. Thank you.